Acids and bases. We've always been told that acids are bad, right? You burn yourself. Strong acids will do that. In fact, you'll also learn later on that there's acid in your stomach to help digest food. It's called hydrochloric acid. It's got a pH of 2, which I'll explain. It's a scale to see how many hydrogens are in the solution or not. Well, you put a drop of that gastric acid on your hand, it'll come out the other side. It's strong. So we know that there's strong acids. We know it can burn yourself. But there's also weak acids. Okay? I mean, citric acid, you drink that, right? Acetic acid, vinegar, right? But we also have bases. And strong bases will also burn yourself. All right? Bleach is a good example. All right? So let's talk about what this is all about, acids and bases. And what water does. Why is this in the chapter of water? It's about acids. Because you put something in water, things happen. So let's get back to a salt. Remember I said yesterday, a salt. It's not like I want to beat you, right? Not a salt, but you know. So let's just talk about really quickly what an organic compound is and an inorganic compound. We'll talk more about this in the next couple of days also. An inorganic compound is any compound that doesn't have carbon. There's a couple exceptions. Carbon dioxide is one of them. But we'll talk about that later. For right now, anything without carbon is what we consider inorganic, and they're held together by ionic bonds. A salt is any cation other than hydrogen. Sodium, magnesium, potassium. Okay? And a salt is any anion other than what we call a hydroxide ion, which is represented by OH with a negative charge. Electrolytes are basically ions, and they conduct electricity. If there's charges in there, it will conduct electricity. Technically speaking, and I don't want you to do this at home, technically speaking, if you get distilled water, which is water that has been removed of all its charges, salts and you know, like sodium and chloride and stuff, and it's just plain water in there, if you put that distilled water in a bathtub, and you drop an iron in there that's still plugged in, and you put your finger in there, you won't get electrocuted. Don't do that experiment at home. Because there could be electrolytes on the tub itself that gets washed into the water. Okay? I'm saying in a controlled experiment, it doesn't conduct electricity. So an acid is a substance that gets dropped into water and dissolves and releases hydrogen. A strong acid is going to release a whole bunch of hydrogen ions. It obviously will conduct electricity better than a weak acid. That's what burns. They have something we call a complete dissociation. What does that mean? All right, let's talk about hydrochloric acid. Hydrochloric acid is abbreviated like this: hydrogen and chloride. Hydrochloric acid. That, when you put that in water, all of it will dissociate like this. Okay? And you have that hydroxide shell over it that I showed yesterday. You put a salt in water, the sodium and the chloride gets surrounded by water molecules. In this case, it's not that, it's the hydrogen will be surrounded by water molecules and the chloride. But the thing is, it's 100%. All of this yield sign. All right? Then we have a weak acid. And a weak acid releases less hydrogens, of course, but you have a partial dissociation. What happens here is we'll give you when you mix carbon dioxide with water, okay, that's going to be making something called carbonic acid, which is this. Now, it doesn't stay like that. It dissociates when it's in water. But it goes through this intermediate. And then this carbonic acid will turn into hydrogen ions and what we call bicarbonate ions. It's really big, like going like this. Now, for now, look what's happening here. You see the big difference besides, but let me just erase this now. Now you understand where that carbonic acid came from. But you have this carbonic acid dissociating here. All of this turns into that, not here, because of the yield sign. Half of it goes there, and half of it stays here. It becomes a teeter-totter. It's only partially dissociated. Does that make sense? Okay? Now, this is what's nice about this. If I put more carbonic acid on the reactant side, which way is this reaction going to go? To the foam or to the switches?
Wait, did you say that again?
To the foam, right? That way. But I could also add things to this solution. I could put more hydrogens in here. Now, if I put more hydrogens in this reaction, is it going to go to the switches or is it going to go to the foam? The switches. You're creating this teeter-totter. It's making a balance. It needs to become 50% on one side and 50% on the other side. If I add more hydrogens here, theoretically, you will have, let's say, 70% of stuff there, but now you're only going to have 30% over here. That's not stable. How do you make it 50-50? Which way is the reaction going to go? That way, until it becomes 50-50. This concept was put together and theorized by, I guess, well, I know it's a name because it's what it's called. It's called Anhydrase principle. Don't worry about it. I won't ask you about that. But this thing about the idea that you put stuff on this side goes that way, stuff on this side goes this way, so that it becomes 50-50. See, what's happening here, you're not really changing the amount of hydrogens, really. Even if you're putting more hydrogens, it's turning it into this. You can do the other way, too. I can remove hydrogens on this side. I can remove it on this side. Theoretically, this becomes 30% because I removed some of the stuff. But then, net-wise, if there's less here, there's got to be more on this side. It's 70. So which way does the reaction want to go? If we remove that, does it go that way or this way? What we've created here is something called a buffer. No matter how much hydrogen you put in or take out, it's keeping the pH, the amount of hydrogens, the same. The buffer. Is that clear? Okay? We'll talk more about this too. So here's the reactions up here, right? So there's our strong acid, and what I showed you breaks up, the hydrochloric acid breaks up into hydrogens and chlorides. We'll do the strong base, but that's basically the same thing, except we're not dealing with hydrogens, we're dealing with hydroxide ions. And the weak acid, carbonic acid, the one I put up on there, will break into hydrogen ions and bicarbonate ions. I call it bicarb by short. But it's equilibrium because you've got 50-50 on either side. A base, when dissolved in water, releases these hydroxide ions. If you understand this concept, it's the same thing, so I'm not going to really repeat it. A strong base releases a lot of hydroxide ions, which means it has less hydrogens. And it's complete dissociation, like sodium hydroxide will break up like that. All right, a weak base releases less, and it's the same concept. But we have a lot more acids to really deal about, and I'm going to spend a little bit more time talking about this carbonic acid too. Okay? So you put hydrochloric acid in water, it will dissociate. Look, hydrogen's coming out. You put potassium hydroxide, which is a base, you put that in, it'll break like this. And a salt, since there's no hydrogens or hydroxides, it's anything but. Clear with that? All right, let's talk about the pH scale. All right? I'm not going to show you how to get to the pH scale. I don't even know if the chemistry people are doing that. You've got to learn about Henderson-Hasselbalch's equation and all this. Just take my word for it. They did all the calculations, and I'm giving you now the meat and throwing out the bad person. All right? It's too much for here. But pH symbolizes the amount of hydrogens in a solution. You have this pH scale that ranges from 0 to 14. 0 to 6.99 is an acid, with 0 being very strong and it has a lot of hydrogens, whereas 6.99 very weak, very few hydrogens. 7 is neutral, distilled water. There's no hydrogens or hydroxides in it, it's just that. It's equal. And a base would be 7.01 to 14, with 14 being a very strong base. And it's on a logarithm scale, which, again, I'm not going to go into dealing with that over here, okay? So you can see, and we're going to do an experiment on this. I think the lab experiment is Monday, right? It's the ocean that we're doing in pH. Right, so you'll be working with this also. And we're going to have different things, and you can actually see what the pHs are. I mean, there's our distilled water, right? Pure water, which is 7. When you look in the beakers over here, you'll see that there's the hydrogens and the hydroxide ions are equal with each other. But as we get lower in the pH scale, going from, let's say, tomato juice to vinegar to lemon juice to battery acid to hydrochloric acid, virtually 0, you'll see there's a lot more hydrogens in there than hydroxide. And similarly, as we go the other way of the scale, becoming more basic, or another word we say is alkaline, human blood is a little bit of basic, not so much, but 7.4. But you're going to realize later on that 7.4 and 7.6, that's a big difference. And you will be sick if that happens. So ocean water is over there, ammonia, bleach, and so forth. You'll also see in the beaker here that there's a lot more hydroxide ions than you do hydrogen ions. Right? There's another one showing other things where milk falls in and stuff. All right? The only joke I could get. You're a 10 on a pH scale, maybe, because you're basic. So, the buffers that we were talking about, they resist change in pH. If you add things to it, hydrogen or hydroxide, it'll fix it. So when hydrogens are added, the buffer will remove it. If the hydrogens are removed, the buffer puts it back in. So a buffer is any substance which minimizes any change in the hydrogen following an addition of an acid or a base. Now, this reaction, memorize. You will be using this, not just in here, but for everything you're probably going to be doing if you stay in biology or chemistry. If you're thinking about getting a tattoo, this is the tattoo to get. Not that I'm encouraging tattoos. I keep on saying it to students, and when they say someone's going to have it on there, and I'm like, I had nothing to do with it. But it's a very important reaction. Well, let me go to the next. I'm going to write it up on the board too. All right. This is what I just wrote underneath. Put the whole thing in. I'm going to show you how you're going to use that. So blood, like I said, normal levels is 7.4. All right, with an average of 7.35 to 7.45. And any change in the above will change your body. And things, I'm going to show you how your body changes this. Well, luckily you have something that's going to fix it. And it's that buffer. In fact, the enzyme, and an enzyme is anything that's going to speed up a reaction. That reaction on the bottom works by itself, but it takes about days to do. But there's a certain enzyme that will speed it up. We have that, God, probably about 7, 8 places in our body. In our brain, in our pancreas, in our stomach, in our kidney, it's all over the place. But that enzyme is called carbonic anhydrase. Now, this reaction that I showed you just before doesn't have a name to it. I don't know why no one coined a name for that. We'd like to just call it the Gamara reaction, but it won't get in trouble. So I guess I refer to it as the carbonic anhydrase reaction, because this is what it does. If in the blood the pH drops below 7.35, that's a condition called acidosis. If it goes above 7.45, you call it alkalosis based on the word alkaline. And you will be sick. You will realize that if your blood is very acidic, it will break down proteins and you won't be feeling well. If it goes down really low, you just die. Now, I just want to also mention, too, that our bodies always produce acid. We're going to talk about some of these acids later. Amino acids, fatty acids, lactic acid. So our bodies go through more of an acid stress than basic stress. But there are times when we'll go through base. But our bodies produce more acids than bases. Okay. So let me do this little interactive thing for you guys. I'll show you how you can apply this stuff in what you do. Okay. So the reaction again that's an intermediate. It doesn't like to stay like that in our body. They immediately change into something else. But it has to do that step first. And that will then turn into hydrogen ions and bicarbonate ions. And carbonic anhydrase is in here. Okay? This reaction will occur without that, but it'll take days to do. You'll be dead by the time that happens. So we have this wonderful enzyme that will speed it up. Now, this is what's going to happen. You do this, I know you do this. All right? You're running a marathon. You're running. And all of a sudden, you got this pain here. What did you just make? Which we'll talk about in another lecture. You got that pain that you just produced because you just ran and like, what's that pain right here? What is that? Lactic acid. We'll get into that. You made an acid. So that goes into the bloodstream, and all of a sudden, these hydrogens are going to go up in your bloodstream. Right? You with me? Okay. If we increase the amount of products over here, reactants per se, which way is the reaction going to go? Is it going to go to the switches over there or to the foam? Switches. So this reaction is going to go all the way over here. Are you going to make more carbon dioxide or less? More. When you're running a marathon, are you breathing like right now, what you're doing? Or are you... Right? You're breathing faster. You're producing a lot of carbon dioxide. You can't hold your breath. Your body won't allow you to do that. Your body needs to let out that carbon dioxide. And water vapor goes out there too. That's why you're doing that. You're creating a way to remove that hydrogen out of your body and making it so that becomes 50-50. Why? Many reasons, but that's why you breathe heavy during that time. Let's talk about, hesitant to do it in here, but I think it'll work. I think you guys will follow me. Let's talk about someone who's got emphysema. That's someone who has problems exhaling. They're big smokers for 20 years of their lives. Their lungs, they are not working. They can't exhale all that air anymore. It won't go out. They don't have the capacity to do that. So look what's going to happen to a patient who's got emphysema. And you've probably seen these patients. Go to Walmart. It's usually someone, I'm not making fun of them, but I just look at people around and I can see. They usually have the oxygen tank over here. They're leaning this way. They usually have their pursed lips. And breathing like that. They're hunched over because they're trying to make their chest smaller, to try to push out more air because they can't get the air to push out. So they're doing this. Heavy smokers. 99% of people have emphysema, heavy smokers. So they can't get the carbon dioxide out. So look what's going to happen. If they, I'm not asking them to run a marathon, but if they need to walk from here to that door over there, that is like a marathon to them. And by the time they get over there, they're going to be in pain because they got that lactic acid. Now look what's going to happen here. Their lactic acid goes up, right? This is supposed to be over here 50%, and over here is supposed to be 50%. But this is going up, just like you run a marathon. So now this is going to be like, I'm just putting numbers here, 70%, which means net-wise, you put this all together, it's only 30% here. Which way is the reaction going to go? To the switch or to the door? switch, just like before. So it's going to go this way, but look, with a person who's got emphysema, they normally would be blowing this out. But they can't because they have that lung disease. So what's going to happen now to the amount of carbon dioxide in that person's blood? It goes up. It goes skyrocket up. Now it's all switched. Now this is going to be 70%, and this will be 30%. Which way is the reaction going to go now? That way. What's going to happen to the amount of hydrogens in their blood? Go up. So they have a condition called alkalosis or acidosis. Acidosis, because of all the hydrogen. Now, we have another organ, and it's way over, it's over here. We have another organ to get rid of this, called the kidney. However, that will take days to do. And the problem is, emphysema doesn't get any better, so they got their lungs that aren't working. As long as they got a kidney that's working, they'll be living, but it's going to be tough for them. Because it takes days, because this is not going to get any better. Now, if you have someone who has emphysema and kidney disease, you're screwed. All right? Do you understand what I'm saying? You're going to have to be on dialysis, and there's a lot of other things. Not trying to make doctors out of you, but I want you to understand that you see this. You do this all the time. Not the emphysema part, but you're producing the carbon dioxide. So your body's always producing carbon dioxide. You're going to find out when the carbon dioxide comes out, our plants are going to take the carbon dioxide, change it to their food, they release oxygen, we take the oxygen, we put it, convert it into energy, and then we get carbon dioxide that comes out. It goes, see, that's a big cycle. But does that make sense? Yeah? You're on your way for anatomy and physiology. All right. We good with that? You understand how you understand this whole reaction here? Because you're going to see that reaction again, not so much in like emphysema and stuff, but you'll see it later on in the course too. We'll talk about global warming and all that stuff, because it's important that you see a lot of carbon dioxide comes from places. Okay? You understand that, right? Yeah. Good. Because I had some teachers that said, they're not going to be ready for that. I think they'll be more ready for this than the other stuff. But you seem to really get this stuff. Right? Good, good. All right. And we go into much more detail with this when we get to other biology classes. But at least you see a little start of it, what this is all about. There's some parts of biology and science you just have to memorize facts. But it's the concept, and I see the twinkle in your eye when I start doing this, that you get it. Just hope you remember it. Right? So that's what that is. You're going to see a lot more of this kind of stuff.